हाँ हेलो सर मी लेक्चर मध्ये आहे. नमस्ते नमस्ते हां बोला की नंतर फोन करू. Hello, good morning. Am I audible?
Yes, sir.
So today we take a review what we discussed last time. So last time we discussed second topology of multi-level inverter, and that name of the topology is a flying capacitor multi-level inverter. And we have discussed the circuit configuration for 3 level as well as the 5 level configurations. And our observations, if you see it here, for each particular a state, you can call it a level. For a particular level, VAO level, we are having multiple switching combinations are possible. That is one of the peculiar characteristics of this flying level 5 level flying capacitor multi-level inverter. If you see here, particularly we are considering case of 5 level flying capacitor multi-level inverter, whereas plus VDC by 2 and minus VDC by 2, that VAO level we don't have a redundancy of switching of the devices. But if you consider the case of plus VDC by 4 and minus VDC by 4, in that case, we are having the three possible combinations of which we can obtain the voltage VDC by 4. Whereas if you see it here for 0, VAO equal to 0, we are having almost 6 possible combinations are possible. So that is the one of the important feature of this, and this feature we can utilize to balance the capacitor voltage. But now here we have seen that now requirement of capacitors for this one leg. Normally our inverter is 3 leg, so out of that we consider for one leg our number of capacitors required is m minus 1 multiplied by m minus 2 divided by 2, where m is the a level. And if you take m equal to 5, so 5 minus 1 multiplied by 5 minus 2 divided by 2. So 4 into 3 divided by 2. So it is a capacitors will come out to be a 6. And we have seen that these are the 6 capacitors. Whereas this DC link capacitors for splitting the DC link, they are not included. What we are calling the capacitors will be these capacitors we are talking. And for 5 level, we require capacitors will be equal to 6 capacitors. But here one of the drawback is particularly the size of capacitor will depend upon the how much is the current rating of the inverter. And so capacitor is a passive component and size is bigger, so the inverter will become bulky. That will be there, and inverter control will be complicated. So that will be the features of this. And third topology, what we discussed yesterday, was a cascaded H bridge multi-level inverter. So our H bridge is nothing but a full bridge inverter, single phase full bridge inverter consisting of 4 devices. That single phase full bridge inverter, another name, it is called as the H bridge. And here this 3 phase 3 level. So there will be each load we are supplied from a separate H bridge here. So this is a H bridge for phase A load. This is a H bridge for phase B, and this is a H bridge for phase C. So we are having one H bridge for each load, and we have seen it here. So this H bridge we can have a now here number of levels 3 we are calling in terms of a phase voltage. So we are 3 loads we connected in star, and we are in VAN, VBN, VCN are the 3 phase voltages. And here we are getting a 3 level means 3 levels in the of phase voltage. And if you see it here, if you see S1 and SA1 and SA2. I am taking about the phase A. Other phases will be also having the same. So here SA1 and SA2 are on. We say that the positive upper terminal positive is connected to A of the load, and negative through SA2 will connect it to the neutral. So here when SA1, SA2 on, our load voltage VAN will be equal to VDC. And if upper two are on, let us upper two is SA1 and SA2 are on, and then we have seen that our load is shorted. Our load is shorted through this upper two, so we get the zero voltage. Or lower two are on, SA4 and SA2 are on, then also our load neutral and A point, they will be shorted together through these two devices, and we get the zero. Whereas whenever SA3 and SA4 are on, we get the negative VDC. So this is a particular configuration. Okay, this is a particular configuration where we get three levels in the phase voltage. Here we are having a H bridge, but they are not cascaded. So here I am given the title as Cascaded H bridge multi-level inverter, but here only one H bridge is we have shown it here because we are having a three level, and one H bridge will provide the three voltage levels in the phase to neutral voltage. Now next, if you are having, we want to have cascade, means connected the H bridges in series. So this is for phase A, phase B, and phase C. And now here we have seen that in particularly for phase A, we have connected the two H bridges in series. For phase A, we are connecting the two H bridges in series. Similarly, here B phase and the C phase. And here one important, we can call it as a drawback of cascaded H bridge multi-level inverter, that for each H bridge we require a separate DC supply. For each H bridge we require a separate DC supply. And here we have seen that one H bridge, first H bridge, this will give provider three levels, and after that whatever H bridge you add, they will give a change in level by 2. So here whenever we are connecting the two H bridges in series, the number of levels will be 5. If you connect three H bridges in series, first will give a 3, then 2, and then 2. So we are having a, when three H bridges are connected in cascade, we get a 7 level. So similarly, we can have a 9 level and other things. So this will be here. We have shown the circuit, particularly for 5 level, 3 phase 5 level cascaded H bridge multi-level inverter. And in that case, we have seen that each phase is required two H bridges to be connected in series. This is case for phase A, this is for phase B, and this is also for phase C. Now here we are getting the levels. We have shown it here. Number of levels are 5. In this is a particularly phase voltage levels, not the line voltage. So we are talking about the phase voltage, and phase voltage magnitude will be when these two DC sources will be added together and appear as a positive across the load. Two VDC sources we connect in series with the help of switching of these devices. With the switching of these devices, we connect two H bridges in series. Sorry, we connect these two DC sources in series, and they will appear across the load. They are series additive and appear across the load. Then we'll get the twice VDC. Here, in case of one of the DC source is bypassed, either switching on lower two or upper two devices, one of the DC source is not taking connected across the load, only one DC source is connected across load with positive polarity, then we'll get the VDC. Now here we are discussed how to get the zero voltage across the load. In that case, the two voltages VDC upper and lower, they will be added in series but in opposition. Their polarity will be opposing, and this opposing voltage polarity, series opposing voltage polarity, will appear across the load, and series opposing polarity, that will be resultant will be 0, and voltage across it will be a 0. And negative VDC we can obtain when only one DC source will appear across the load, other is not taking part, and one voltage source that appearing across the load with reverse polarity. Neutral point will load neutral point will come to the positive of the DC source. Then we get the minus VDC. Whereas twice minus VDC, two are in series additive, but they are appearing in the negative across the load. So here, in case of three-phase, five-level cascaded H bridge multi-level inverter, we are having the five levels. And how to obtain these five levels? Okay, we will just discuss the case. So here SA1, SA2, SA3, SA4. We are given the names here. If you look at the names, we are not a particular sequence is followed. Here SA1, SA2, SA3, SA4, and the complementary pair concept is present here. Complementary pair concept is here. So SA1 is upper device, lower device of that lay inverter we can call as SA1 star. SA2 is here, complementary device will be SA2. Similar case for SA3 and SA4. Now we are considering the case when SA1 is on. So we'll start here SA1, SA2. So we'll just see it here. So let us assume that our SA1 is SA1 and SA2 is on. Okay, I will just start here. Then we can see the direction. Our device on is SA2. Okay, I'll follow this. Then this will be go to a DC source. Okay, then through SA2, sorry, SA1, it will go to the other. Okay. Then we are having SA3 and SA4. So I'll go for SA4. From SA4, it will go to the other DC source. From this DC source, upper this. Then from SA3, it will be coming to the load. So this is our path. When, how is the current path? Whenever SA1, SA2, SA3, SA4, these four devices are turned on. So SA1 is on, SA2 is on, SA3 is on. We have shown this. And now we have seen, if you observe the polarity, this is our VDC plus, okay. VDC plus, and then if you see it here, this plus, if you connect to the minus of this, and then this. So it means that these two DC sources, are connected in series. These two DC sources are connected in series. So voltage appearing across this will be a VDC plus VDC. Now we consider the reverse case. Reverse will be a just minus twice VDC we can consider. Here minus 2 VDC, we have seen that just our, these are two connected, these other devices, whatever we have shown it here, they will be turned on, and these voltages are again additive but appear in the reverse direction across the load. So that will be our particularly a twice VDC case. Okay, other two devices, four devices, SA1 star, SA2, SA3 and SA4, both the VDC1 and VDC2 or VDC and this VDC will come in series, but they will appear opposite directions as compared to this. That's why it will be a minus twice minus VDC. Now consider the case of plus VDC. Is it right? Now we can use this for plus VDC, the circuit we can use. And in that case, a plus VDC, we have seen that SA2 and SA4 or here, sorry, SA1 and here we can take it SA2 and SA1. SA2, A2 means SB2, this switch is on, and SA1 star, this switch is on. Okay. So now here, so these two switches are on. How is our path? So let us take this SA1. I will go from this. So it will be this switch is on, then this switch is on, then this switch is on, and then it goes to this. Okay. And then we are having 3 and 4 are on. Okay, 3 and 4 are on. So 4 and then 3 is on, and then it will go back to this. So here what it shows, it will show that lower DC voltage source is bypassed. So this is not connected across the load here. In case of VDC, this is not connected across the load, but this is only connected across the load because this lower two devices, the SB1 star or SA1 star and SA2, these two are on. Okay, so that whatever this current, it will be a this DC source is not taking part in this case, and only one DC source is coming across the load with positive polarity, and that is why this particular we get a plus VDC level. This particular circuit, you can say, we can obtain for a plus VDC at the load. Now let us consider the case how we can go for a zero, zero voltage level. So for zero voltage level, let us again draw the, for you will use the third case. So third diagram we can use. So 0, upper two are on. So SA3 and SA4 are on. So these two are on. Okay, these two are on. And lower cases we are having SA1 star and SA2 star. These two are on. Okay, these two are on. So now how the path, we'll just trace it here, this from this. Okay, we can just make this path, then we can see the direction. So this, then this, then this. So if you see it here, this is the path we are having. And now here, so here if you start from this one direction, so this is the negative of the lower voltage is connected to the negative of the other. Okay, negative of the other. So here this is a negative. I'll just check 1 minute. As this negative of the one is connected to, both negative are connected together, means they are having a series opposition. These two voltage sources, they are having a series opposition. They are having a series opposition particularly for this, and because of that, okay, output voltage will be a 0. So this is the case we have shown it here, what configurations is required for switching of this. And now we can just get the table of this. Okay, we just SA1, SA2, SA3, one leg, and SA1, SA2, SA3, SA4 star, and what levels we can get it here. So this is, we have shown it here, which switch will be on and which switch will be off. And now this particular table, and if you go for a table what we have discussed earlier for diode clamped multi-level inverter, the table is one and the same. Table is one and the same. 1 minute, where I just okay, that table now at present, okay, is same, but I want to show it, but okay. So this table is same for 5-level cascaded H bridge and 5-level diode clamped multi-level inverter. The table is same. So what is it interpretation? The same control technique, same multiple carrier PWM we can use for 5-level cascaded H bridge multi-level inverter. So whatever control technique we discussed for 5-level diode clamped MLI, same can be used for 5-level cascaded H bridge inverter. Only thing is that you should, just while giving the signals, you can follow the conventions here. Whatever SA1, SA2, SA3, SA4. And what is the convention in the diode clamp. So if you just follow the same convention, then same control can be used for cascaded H bridge multi-level inverter as well as the neutral point clamp inverter. So this is the PWM technique, same we can use. So we are not going to discuss about it. Now we are having few more cases here. Okay, so how we get the 7 level? So first bridge, H bridge will give 3 level, next 2, next 2. So 3 plus 2 plus 2. So this will be a 7 level, we can get it. And phase voltage levels for 7 level, 3 voltage sources in addition, 3 VDC, 2 VDC, VDC, 0, minus VDC, twice VDC and minus 3 VDC. So here we can add any numbers. If you add one H bridge in series, you increase your level by 2. Now here we are having some techniques to have. Now one of the is there. Suppose we want to operate all the switches at power frequency. Here we have shown already in cascaded dark lamp multi-level inverter. This is the one waveform we have shown. Here we are having a PWM switching. Inverter is switching at a 1 kilohertz or 10 kilohertz. And when we are having a high switching frequency, definitely switching losses will be more. And so our interest is we want to operate the switches at lower frequency. But if you operate the switches at lower frequency, we are having a problem of harmonics. Okay. So here we are going for one another technique. Here we can get a better quality waveform, but at the same time we are operating the device at lower switching frequency. And here this will be the case we have considered here. We have shown the one leg of the 9 level inverter. So 9 level means first is 3, 2 plus 2 plus 2. So this will be a 9 levels we can obtain. Okay. But now here what we are doing is all these switches we are operating at a power frequency. Let us assume that our frequency is 50 Hertz. So all the switches we are operating at a 50 Hertz. Means our switching frequency is less. So what is benefit of low switching frequency? What will be benefit when we are operating the inverter at low switching frequency?
Less switching losses.
So there will be switching losses will be less. Normally in device, two losses are major losses. Normally in the device, two losses are the major losses. What are these two? One is conduction loss. When device is on, there will be a voltage drop across it and current flowing through it. And because of that, that loss we can call as a conduction loss. One loss is the conduction loss and other loss is the switching loss during turn on and turn off. And when switching frequency is high, definitely the switching loss will be high. And to reduce that loss, we want to operate the device at lower frequency. So this is here we are discussing one such a technique that is possible with the help of a cascaded H bridge inverter, multi-level inverter. Now here if you observe this waveform, so here we have seen that we can construct the output voltage. You are knowing how we construct the output voltage in case of cascaded H bridge multi-level inverter. We can just connect the capacitor or DC sources in series. Some sources by connecting the two. Here if you see it here, if you go back, how we get the here 3 VDC. 3 VDC is adding these 3 voltage sources. 2 VDC means we are having two DC sources in series and one is bypassed. VDC is 2 is bypassed, only one will be remaining like that. So similar configuration we are having. So either we are adding the DC voltage sources, we are changing the levels. Similarly here we have done this. If you see here, this is the first, let us go for lower this. And if you see this period, the period at which we get a positive voltage level when two devices are on. So in a positive, this period, if you see it here, this much period the two devices are on. So let us assume that these two devices are on, so we want to have positive voltage. We want to have a positive voltage. These two devices are on, but they are on almost. Let us assume that the 180-degree period, out of that they may be present for 160 degrees. Okay, it may be a present for 160 degrees. Now this so these two switches will be on for 150 degrees. Next, let's assume these two switches of the second H bridge, they will be slightly less, maybe a 140 degrees. Okay, there may be a 140 degrees. Then third, we have seen that this, okay, connected with this will be a just maybe 100 degrees, and this may be a 50 degrees. So this and we can make a logic such a way that our resultant output voltage will be a staircase type. Resultant output voltage will be a staircase type. And this particular will get, now here what is benefit? Our output voltage waveform is better, but at the same time our switching frequency will be power frequency. So our devices are operating at less switching frequency. So power loss, switching power loss in the device will be less. So this is the output voltage waveform in case of our this power frequency switching. Whereas this waveform we are saying, this just we are copied from neutral point clamp multi-level inverter. We have seen that we are having a high frequency switching. Okay, maybe 10 kilohertz, but here we don't have it with switches are made on at a power frequency, or switching frequency of devices used in this case will be just the 50 hertz, whereas here this waveform we are getting the switching frequency will be in kilohertz. And this is one technique we are having where we can make a balance between, that is the benefit of multi-level inverter. We can make the balance that, okay, we can reduce the switching frequency. Why want to reduce the switching frequency? We have to reduce the switching frequency to reduce the losses. So the inverter efficiency will be higher. So we are reducing the losses. At the same time, we get the better quality waveform. And that is one of the technique we have just shown it here. Now another technique here, and this is a particularly what is number of levels for this inverter. The phase voltage we are having here, it is a 5 level. Okay, here we are having a 5 level, a 3 level, and this. And if you see it here, earlier cases, in all earlier cases, whatever the voltage is applied to each bridge are equal. Okay, here, or whatever our case here, the voltage is applied to each H bridge is the equal value of voltage we are applied here. Now here we are going for something different. And in this case, we are going for a 5-level cascaded H bridge multi-level inverter. And here upper, okay, voltage will be half of the lower voltage. So our VC2 voltage across the capacity, or here we are having a DC source which is having equal to VDC magnitude, whereas here DC source which is having a magnitude of VDC by 2. Okay, so we are doing this so that we can get this type of output voltage waveform, because this particular give a positive voltage, we switch on these two devices for this much period, then these two devices will be, so this DC is coming to the load as the load during this period, and if you add these two, this will be our resultant output voltage waveform. So this is the one benefit we are having, where we are having a different voltages to the H bridge. So DC voltage applied to H bridge is different. What is intention? Why we are doing this? Why we are applying a different DC voltages to H bridges? What is intention?
So that output can resemble closely to the sine wave.
Okay, output will resemble to the sine wave, and at the same time our switching frequency will be the power frequency. So we have to compromise both things. Our losses should be less. At the same time, we are getting the better quality output waveform. Now let us go for one another. Various options are available. So what if you look at the two bridges? What difference you can get this? Is it visible? We are shown the two bridges. It is again a 5 level, one leg of the 5 level inverter. So what is the difference you are getting between the two bridges, H bridges? What is the difference between the two H bridges here?
IGBTs are present only in the upper edge bridge.
So here IGBT is in the upper. And which device is at the lower?
Thyristor.
Okay, so it may not be a visibility is problem. Okay, it will be a GTO. At the gate we are having cross. Suppose what is the GTO symbol used? I will just show it here. A GTO symbol used here. Gate turn off thyristor. So this is our thyristor symbol. Is it right? And if you just make a cross here on the gate terminal, then that device you can call as GTO. So this is the GTO symbol, and lower I am just drawing is the thyristor symbol. Okay, there are so many. So this will be one way to represent the GTO. This is the so this upper device symbol. This is our GTO. Lower is our thyristor. GTO can be also shown. I will draw the another symbol for GTO, where we can show it like this. We can show the two gates current in that. Okay, so one is going inside, okay, turning on, and other is turning off. This type of symbol is also possible in case of a GTO. So here what I want to show is, here we are using the GTO and here we are using the IGBT. That may be a high power applications. Let us assume that. Why we are using two different devices? What will be logic? One bridge we make a gate turn off thyristor, and other bridge we can use the IGBT. So GTO we can operate at low frequency. Okay, these devices we cannot operate in kilohertz range. Okay, maybe we are operating 1000 hertz maximum. Maybe a GTO. So GTO switching frequency is less, whereas IGBT can operate in kilohertz range, 5 kilohertz, 10 kilohertz. So IGBT is operating in 5 kilohertz or 10 kilohertz range, but this GTO they are operating at a lower frequency. These devices are suitable for low frequency applications, but they are having a higher voltage and higher power ratings are available. So particularly in power system applications, if you go for a STATCOM, or you can call as a, okay, have you studied STATCOM now presently?
No, sir.
You are having power quality subject?
Yes.
Yes. So in that, okay, you are having a reactive power compensation. Have you heard word reactive power compensation in the power system?
Yes, sir.
Yes, sir.
So what is purpose of reactive power compensation? Why reactive power compensation is required? Why at a particular bus we have to provide the reactive power? Why at particular bus? So we have to provide the reactive power to support the voltage or to maintain the voltage of that particular bus. So for reactive power compensation is required to maintain the voltage profile. Okay, we are going to discuss that application afterwards. But now here, in that case, whenever we are going for high power applications of power electronics in power system, in that case, GTO may be a device is used. So here, one bridge we use the GTO because it is suitable for low frequency application, and IGBT is suitable for high frequency. So we make a hybrid combination. So this will be a PWM switching we can make for this IGBT H bridge, and it's the power frequency switching for GTO based H bridge. So GTO based H bridge is operating at a power frequency. We are operating this H bridge at a power frequency. Switching frequencies, these two devices will be on this much duration, other two will be on this much duration. Whereas this IGBT, we are making it as a on and off. That will be PWM switching. We can do it here. And then resultant waveform we are having like this. So this is also a combination possible. One bridge will be operating in the PWM mode and other will be operating in the square wave mode, we can call it. Power frequency mode also you can call as a square wave mode. So one will be operating in the square wave mode. The GTO based H bridge is operating in the square wave mode or power frequency. It will be operating at a power frequency, and this will be operating at a higher frequency, and we get a hybrid result combination. So we can compromise on the losses also. Instead of losses taking place in both bridges, one bridge will have less losses, other will be higher, but at the same time we will get a better quality output waveform. So this is about all about our particularly the multi-level inverters. So we are discussed the three topologies of the multi-level inverter. First is dart clamped multi-level inverter. Second is flying capacitor multi-level inverter, and third is cascaded H bridge multi-level inverter. And now we are going to discuss the applications of this multi-level inverter. Any question, general doubts regarding multi-level inverter? So we discussed three topologies. We'll share the PPTs. So any question?
No, sir.
So let us go for our applications. Okay, so one of the applications of a multi-level inverter we are having. Now if you see it here, our input is DC. Is it right? If you see, is it visible?
Yes, sir.
Yes. And this particular bridge before the transformer, okay, before the transformer, you can have a multi-level inverter, you can call it. Configuration will be single phase multi-level inverter. Okay, this configuration. Then we are having a transformer, maybe step up or step down. Okay, and then we are having a diode bridge, and then we are having a LC filter, and then this. Okay, and now we want, so here from fixed DC, is it okay? So from fixed DC, we want a variable DC. Is it clear? From fixed DC, we want a variable DC, but that variable DC should be isolated. So output should be isolated from input. So isolated DC to DC converter. This whole configuration we can call as isolated DC to DC converter, because our input and output are electrically isolated. How the input and output are electrically isolated? How we isolate the
Through transformer.
Input is the DC through a transformer. Is it right? This transformer, what should be the frequency of this transformer? Is it a power frequency transformer or a high frequency transformer?
High frequency. Yeah.
So we have seen that this particular, in this case, for isolation purpose, we use the high frequency transformer. Why we are using high frequency transformer? What will be reason why we are going for a high frequency transformer? Now we can discuss the EMF equation of transformer. Is it right? E will be given by, what is the EMF equation of transformer? E will be equal to 4.44 pi mf TPH. 4.44 pi m F and a TPH. Okay, so TPH. Now here, if my frequency is higher, this, if you look at this, so this is our EMF equation of transformer. EMF equation transformer is given E equal to 4.44 pi mf TPH. And out of that, if my frequency increases, voltage per turn will, if you take a TPH here, okay, so E by TPH will be a voltage per turn. So if frequency is higher, voltage per turn will be a more, or we require a less number of turns, okay, for the same flux. And here when the frequency is high, It means that our transformer size will reduce. So high frequency transformer is always compact as compared to a power frequency transformer. There are some different techniques of design the high frequency. High frequency transformer design is completely different than that of power transformer design. Okay, but if you use a high frequency transformer, size will become very compact, and weight of that transformer as well as cost of that will be reduced to a low value. So here this transformer we are used, this transformer is not a power frequency, is up not, it is a high frequency transformers. And this high frequency, we are having this high frequency diode bridge, and if you are having high frequency, then our L and C values filter required at the diode bridge, that values will be also reduced. So here while input given to this diode bridge, here AC, it is a high frequency AC, and because of that high frequency AC, here L and C required to remove the ripple at the output of diode bridge rectifier will be also less. So that is the benefit of high frequency. We can operate at transformer size will become compact, at the same at L0 and C0. The filtering required at the output will be reduced as compared to a power frequency. And now how to control this inverter, a multi-level inverter. And here we are given the logic. Okay, so let us explain this logic. So it is a one leg, you can have a single phase, you can call it. Here what is the configuration? If you look at what type of inverter you can call it? What is this? You can one can say, if you are seeing the diode, if you are seeing at the diode, you can say it will be a diode clamped multi-level inverter. If you see the capacitor, you can say it will be a flying capacitor. So it is a combination of both, we have used it here. A combination of both we have used here. And now let us assume we are having S1 and S2 are on. S1 and S2 are on. So whenever S1 and S2 are on, very simple, the current will flow, okay, through this. I will not use this particular, I'll just show with the laser here. So from S1, S2 on, you see that this will be connected here, it will be going like this. So VDC will come across, positive VDC will come across this. Okay, so this will be here. So here I'll show it, sorry. I will show the path here. So from this plus S1, S2, it will go to the point A. From A, it is a transformer, and from that it goes to this. So output voltage applied to the transformer is plus VDC by 2. So when S1 and S2 are on, we apply plus VDC by 2. When S3 and S4 are on, when lower are on, let us, when lower is on, we have seen it, we apply the negative voltage. This is the negative side, it will be applied to the transformer. So here transformer plus VDC applied when S1 and S2 upper to are on, and minus VDC apply when lower to are. And now here we are making a phase shift control. Here we are making a phase shift control. So here two devices we are having a S1 and S4. 180 degrees S4 is conducting. 180 degrees S1 is conducting. 180 degrees S4 is conducting. So these two are okay, complementary, you can call S1 and S4 here, and S2 and S3 they will be operating like this. And now here let us assume that what will happen whenever S2 and S4 are on. What will happen whenever S2 and S4 are on? So S2 and S4 are on. So S4 I will just show it here. So S4 is on. Okay. This. Then S2 is on. So negative, this diode is not this. Then S2 is on. This, and then this. So here this capacitor is having a VDC by 2. This capacitor will come in series opposition with this, and so the voltage applied will be 0. So whenever S2 and S4 are on, whenever S2 and S4 are on, we have shown that we'll get the 0. Similarly, S1 and S3 are on. If you see it here, S1 and then S3 will be on. Again, this capacitor will come, and then we'll get the output voltage will be a 0. So this is a logical table, you can call it. When with respect to this diagram, we are having S1, S2, S3, S4 devices, and when S1, S2 upper 2 are on, transformer is supplied plus VDC. Sorry, here you can correct it. I will correct a plus VDC by 2. Okay, here it will be a plus VDC by 2, not VDC. So will be a corrected this. It will be a plus VDC by 2. Similarly, here it will be a minus VDC by 2. So in S1, S2 are on, transformer applied voltage will be plus VDC by 2. S3, S4 on, transformer voltage will be applied minus VDC by 2. And whenever S2, S4 are on, 0, and S1, S3 are on 0. Now here we are having S1 and S4 are complementary. S2 and S3 we make it complementary. 180 degrees S2 is on, 180 degrees S3 is on. So here, so now this, okay, this particularly S1 is on for 180 degrees, S4 is on for 180 degrees. They are sharing one cycle. Similarly, S2 is on for 180 degrees and S3 is on for 180 degrees. And there, these two, we can just make a forward or backward here. Now here we have shown this particular portion, we have seen that S1 and S3. This S3 will be coming it here. So whenever S1 and S3 are on, here whenever S1 and S3 are on, we get a 0 voltage. Similarly, whenever S2 and S4 are on, S2 and S4, if you see it here, this is S2 and this is S4 is on, we get the 0. And one waveform we can move the forward. As this waveform is moving forward, let us assume that what will happen to the output voltage? Let us S2 and S3, we move in the forward direction. This S2 and S3, we move this direction. What will happen to the output voltage? This we keep as it is. S1 and S4 will keep as it is. S1 and S4 we keep as it is, but S2 and S3 move some 90 degrees forward towards the right. What will happen? What will happen if you move 90 degrees? This
output voltage will also shift to the right.
No, then what will happen?
Output
this overlapping of S1 and S3 will increase. When overlapping between S1 and S3 will increase, then voltage will remain 0. Similarly, overlapping between S2 and S4 will increase. If you move this, now I will just show the waveform how it will be. The waveform will be, now the width of output voltage, now it will be something like this. Red I am showing. Okay, because overlapping will increase. And because of that, our output will be something with a red. Okay, with a red, something like that. So the output width will go on decreasing. If we move this S2, S3 in the forward direction, if you move one that we can call as a phase shift control. So S2 and S3, if you move it to a forward direction by 30 degrees, then correspondingly 30 degrees our overlapping will increase. S1 and S3. S1 and S3 overlapping will increase and output voltage will be 0 in that case. So this will be a red waveform. Whenever our S2, S3, this is a shifted by more angle. And this control, how we control the output voltage? We'll control the output voltage by not controlling the switching, but we are phase shift between these two pairs, you can call it. A phase shift S1 and S4 we can call as one pair, S2 and S3 we can another complementary pair, and we make a phase shift. If they are exactly in phase, we get a square wave. If they are out of phase, we'll get the 0. So here a complete output voltage control is possible with this. And this particular application will be particularly for the high voltage application. So any question on this? How we can go for a DC to DC isolated converter using the concept of multi-level inverter? And our control here, how we control the output voltage? Is it a Pulse width modulation control or phase shift control?
Phase shift control.
We are using here a phase shift control. Application may be where we require a high voltage DC. We require a high voltage DC. And one of the application I want to just stress where we require a high voltage DC. So you are having, have you heard the word ESP? Have you heard the word ESP? Electrostatic precipitator. ESP means we are having electrostatic. You can just search on this ESP. This is a particularly used in thermal power plants to dust collection of the boiler. It is a pollution control equipment. Okay, and this will require, okay, we are charge practicals we have to collect. For that we require a DC supply, and this DC supply may be a 100 kV DC. Okay, maybe a 100 kV, 80 kV. So this is our supply is how much? 100 kV DC supply, and current may be 1 ampere. That rating of the DC supply is just the 100 kV voltage is required, but current required is just the 1 ampere. And that type, so this may be an application, one of the application where we require electrostatic precipitator for air pollution control equipment. We are used in case of a thermal power plants. Okay, so for dust collection, we can use it. So that will be one of the application of this, particularly a DC power supply. Now this will be, we are going for a another drive that will be again induction motor drive. You can take it here. And okay, what will be your observations of this? So what will be various observations looking at the diagram? Anybody can comment. Look at the diagram and tell what you are having. So we have seen one transformer. Is it right? Here is a one three-phase transformer. Look at this. Is there any three-phase transformer? Identify the symbol of three-phase transformer. This is a three-phase transformer. Okay, representation method. It is a three-phase transformer. What is peculiarity of this transformer?
Extra winding.
So here, how many windings on the transformer? How many windings on the transformer? Can you make a transformer with 7 windings? My question is, can you make, suppose I want to make a one transformer with 7 windings on it. A single phase, let us take the single phase transformer case. Can I make a one single phase transformer with 7 separate windings on it? Can it be possible? I am having a single phase transformer, okay, with 7 windings on it. Can it be possible? What is your opinion? Can I make a transformer with 7 windings? I have shown 1, okay, and on other side I are having a different 8 windings, okay, different 7 windings. Okay, is it possible? Yes or no?
Yes, sir.
So we can make a transformer with any number of windings on it, but we can give the supply to one winding, and other winding can be work as a secondary. One may be primary. Any one of them may be a primary to which we can use the supply. Other may be work as a secondary. So here, if you see it here, we are having a 3 winding transformer, 3-phase, 3 winding transformer. So how many primary will be there? 2 primary or 1 primary?
1 primary.
Or 2 secondary and 1 primary?
1 primary, 2
What will
secondary.
be? So always transformer we should have, we can feed from only 1. So okay, so we are having only 1 primary and number of secondaries may be n, any number of secondaries. So here we are having the 3-phase transformer and the primary is connected in delta. And we are in 2 separate electrical windings, 3-phase windings. One winding will be connected in delta, other winding will be connected in star. So this is a 3-phase delta star transformer, a 3-phase. So what is purpose of this? Why we require this delta star transformer? Primary is a delta, but why we require two windings at the secondary? One is connected in delta and other is connected in star. Why it is required?
To get
Reduce
different
phase
voltage
shift.
levels.
So we want if a delta here DD0 or DY1. So phase shift between the delta and star is how much? Line voltage phase shift between delta and star is 30 degrees. So this line voltage is of delta and this line voltage is of star. They are having a phase shift of 30 degrees. And here we have seen that with one particularly one delta three phase, we are having a 6 pulse diode bridge. Other we are having 6 pulse diode bridge, and they are connected in series. So it becomes as a 12 pulse rectifier. I think your HVDC have studied this in more detail. So this will be a 12 pulse rectifier. Okay, remaining thing we'll discuss. We are okay. So tomorrow we'll meet to discuss the applications of this multi-level inverter. So we stop here. Any queries? Any questions?
No, sir.
Okay, so we'll meet tomorrow at 10:15 a.m. Thank you.